Before we begin, please turn on your audio and set your monitor resolution to 1024 by 768 for optimal viewing. When you're ready, please click on the play button to start the presentation. Welcome to our presentation on Technology to Support Learning by Bill Bennett and Lisa Fan. We will provide you with an overview of the materials from Chapter 9, along with additional resource information that can be accessed at the end of the presentation. Before we begin, we'll take a trip back to the 1960s to see the beginning of using computer technology to get a better appreciation of how far we've come since then. Computer technology in the 1960s pretty much looked like this IBM mainframe system. Although massive in size, people realized the potential for technology to revolutionize the way we live and work. To be able to appreciate how far computer technology has advanced since the 1960s, click on the hyperlink or YouTube icon to view a video featuring the great-granddad of today's web server and cloud computing systems. This video, called 1963 Time Sharing, a Solution to Computer Bottlenecks, will really make you appreciate your PC. In 1968, Richard Atkinson from Stanford University published research on computerized instruction and the learning process. This paper focused on the Stanford Project, started in 1964, to develop and implement computer-assisted instruction in initial reading and mathematics. In 1969, Patrick Subies and Mona Morningstar from Stanford University published a related article which produced results for 2 computer-assisted instruction programs. For more information about these initial research articles in Learning and Technology, please click on the provided hyperlinks. What we have learned over the years is that technology has a great potential to enhance learning if used appropriately. New technologies provide the opportunity for creating new learning environments that are rich and engaging to the learners. And most importantly, inappropriate uses of technology can be detrimental to learning. Technology does not guarantee learning. Technology can enhance learning if it is used in the correct context. Technology, if balanced by proper instructional design techniques and a good foundation in learning theory, can transform learning into a rich interactive environment for the learner. As we all know, the mere presence of technology does not guarantee learning. Technology has improved instruction and curricula by transforming real-world problems into rich, interactive learning opportunities. In this section, we will evaluate several video-based programs, interactive learning environments, computer simulations, and electronic communication systems that all have contributed to developing new curricula. New curricula offers more opportunities for students to learn than traditional classroom learning environments that simply involve lectures and completing problems at the end of a chapter. New curricula offers a flexible learning environment that actively engages learners and is becoming an increasingly important training tool. Let's take a look at some of the most successful examples of new curricula. New curricula offers more opportunities for students to learn than traditional classroom learning environments that simply involve lectures and completing problems at the end of a chapter. New curricula offers a flexible learning environment that actively engages learners and is becoming an increasingly important training tool. Let's take a look at some of the most successful examples of new curricula. There are 4 different examples of new curricula: video-based learning programs, interactive environments, simulations, and networking students. Please take a look at the chart for more information. The Voyage of Mimi, created by Bank Street College in 1984, was one of the first programs to use video and computer technology to introduce learners to real-life problems. This 13-episode program aired on PBS, taught middle school learners about science and math by following the crew of the Mimi, exploring the oceans, and taking a census of whales. To view a brief video of the Voyage of Mimi, please click on the image provided. Another successful video-based program is the Jasper Woodbury Problem-Solving Series. It consists of 12 interactive videos that presents learners to mathematical problem finding and problem-solving challenges for learners of grade 5 and higher. Learner assessment illustrated impressive gains in understanding mathematical concepts after completing this program. It also improved learners' abilities to work with each other and effectively communicate design ideas to others. To view a brief video of the Jasper Woodbury program, please click on the provided image. New Curricula allows for creation of interactive environments where students can explore concepts in detail. In this example from dnai.org, a learner can actively explore the history of DNA research and technology and view video animations of DNA concepts. The site utilizes animation, video, and audio to engage the learners and is of particular interest for me as I worked on the gene chip and microarray technology shown on this site. If you would like to take a look at the entire website, please click on the provided hyperlink. This interactive environment also provides instant feedback and coaching for the learners. What's different about this example here is that the learner graphically selects the appropriate vector sequence of the DNA that's being studied. If you want to take a look at the entire website, please click on the provided hyperlink. A popular simulation example is Classroom Inc.'s banking simulation. This simulation provides role-playing opportunities for learners to understand the knowledge and skills needed to perform banking duties without breaking the bank. To view a brief video of the simulation, please click on the provided hyperlink. Electronically linking students with peers and practicing professionals allows for Curricula to be readily available with new technology. A K-12 example of networking students is Project Globe, or Global Learning and Observations to Benefit the Environment. This program, where learners collect data in different earth science disciplines, is an international effort to help students learn about their local environments in more than 2,000 schools in more than 34 countries. Other similar programs include Global Lab and the Clovis Project. For more information about these programs, please click on the provided hyperlinks.
In the first generation of computer-based technologies for classroom use, this tool function took the rather elementary form of electronic flashcards that students use to practice discrete skills. As applications have spilled over from other sectors of society, computer-based learning tools have become more sophisticated. They now include calculators, spreadsheets, graphing programs, function probes, mathematical supposers for making and checking conjectures, and modeling programs for creating and testing models of complex phenomena. In the middle school mathematics through applications projects developed at the Institute for Research on Learning, innovative software tools are used for exploring concepts in algebra through such problems as designing insulation for Arctic dwellings. In the Little Planet Literacy series, computer software helps to move students through the phases of becoming better writers. For example, in the Little Planet Literacy series, engaging video-based adventures encourage kindergarten, first, and second grade students to write books to solve challenges posed at the end of the adventures. In one of the challenges, students need to write a book in order to save the creatures on the little planet from falling prey to the wiles of an evil character named Wongo. The challenge for education is to design technologies for learning that draw both from knowledge about human cognition and from practical applications of how technology can facilitate complex tasks in the workplace. These designs use technologies to scaffold thinking and activity, much as training wheels would allow young bike riders to practice cycling when they would fall without support. Like the training wheels, computer scaffolding enables learners to do more advanced activities and to engage in more advanced thinking and problem solving than they could have without such help. Cognitive technologies were first used to help students learn mathematics in 1985 and writing in 1987. A decade later, a multitude of projects use cognitive scaffolds to promote complex thinking, design, and learning in the sciences, mathematics, and writing. The Belvedere system, for example, is designed to teach science-related public policy issues to high school students who lack deep knowledge of many science domains, have difficulty zeroing in on the key issues in a complex scientific debate, and have trouble recognizing abstract relationships that are implicit in scientific theories and arguments. Belvedere uses graphics with specialized boxes to represent different types of relationships among ideas that provide scaffolding to support students' reasoning about science-related issues. A student uses boxes and links within Belvedere to represent their understanding of an issue. An online advisor gives hints to help them improve the coverage, consistency, and evidence for their arguments. Another cognitive example, the Stella modeling environment, grew out of research on systems dynamics at MIT and has been widely used for instruction at both the undergraduate and pre-college level in fields as diverse as population ecology and history. The GenScope project uses simulations to teach core topics in genetics as part of pre-college biology. The simulations move students through a hierarchy of 6 key genetic concepts: DNA, cell, chromosome, organism, pedigree, and population. GenScope also uses an innovative hypermodel that allows students to retrieve real-world data to build models of the underlying physical process. Evaluations of the program among high school students in urban Boston found that students not only were enthusiastic about learning this complex subject, but had also made significant conceptual developments. In another project, middle school students employ an easy-to-use computer-based tool, Model It, to build qualitative models of systems, such as the water quality and algae levels in a local stream. Students can insert data that they have collected into the model, observe outcomes, and generate what-if scenarios to get a better understanding of the interrelationships among key variables. In general, technology-based tools can enhance student performance when they are integrated into the curriculum and used in accordance with knowledge about learning. But the mere existence of these tools in the classroom provides no guarantee that student learning will improve. They have to be part of a coherent education approach. Technology can make it easier for teachers to give students feedback about their thinking, and for students to revise their work. Initially, teachers working with the Jasper Woodbury Playground adventure had trouble finding time to give students feedback about their playground designs. But a simple computer interface cut in half the time it took teachers to provide feedback. An interactive Jasper Adventure Maker software program allows students to suggest solutions to a Jasper adventure, then see simulations of the effects of their solutions. The simulations had a clear impact on the quality of the solutions that the students generated. Opportunities to interact with working scientists also provide rich experiences for learning from feedback and revision. The Smart Challenge series provides multiple technological resources for feedback and revision. SMART has been tested in various contexts, including the Jasper Challenge. When its formative assessments resources are added to these curricula, students achieve at higher levels than they would without them. A computer-based diagnoser program has helped teachers increase student achievement in high school physics. The program assesses students' beliefs about various physical phenomena beliefs that often fit their everyday experiences but are not consistent with physicists' view of the world. Given particular beliefs, sets of activities are recommended that help students reinterpret phenomena from a physicist's perspective. Teachers incorporate information from the diagnoser to guide how they teach. Data from experimental and comparison classrooms on students' understanding of important concepts in physics shows strong superiority for those who participated in the experimental groups. Classroom communication technologies such as ClassTalk can promote more active learning in large lecture classes and, if used appropriately, highlight the reasoning processes that students use to solve problems. This technology allows an instructor to prepare and display problems that the class works on collaboratively. Students enter answers individually or as a group via palm-held input devices, and the technology collects, stores, and displays histograms of the class's responses. This kind of tool can provide useful feedback for students and the teacher on how well the students understand the concepts being covered and whether they can apply them in novel contexts. Computer-supported intentional learning environments provide opportunities for students to collaborate on learning activities by working through a communal database that has text and graphics capabilities. Within this networked multimedia environment, now distributed as Knowledge Forum, students create notes that contain an idea or piece of information about the topic that they are studying. These notes are labeled by categories such as question or new learning that other students can search and comment on. With support from the instructor, these processes engage students in dialogues that integrate information and contributions from various sources to produce knowledge. In the GLOBE project, students inspect each other's data on the project website and sometimes find readings they believe may be in error. Students use the electronic messaging system to query the schools that report suspicious data about the circumstances under which they made their measurement. An added advantage of networked technologies for communication is that they help make thinking visible. This core feature of the cognitive apprenticeship model of instruction is exemplified in a broad range of instructional programs and has a technological manifestation. By prompting learners to articulate the steps taken during their thinking processes, the software creates a record of thought that learners can use to reflect on their work and teachers can use to assess student progress. Several projects expressly include software designed to make learners' thinking visible. In CSILE, for example, as students develop their communal hypermedia database with text and graphics, teachers can use the database as a record of the students' thoughts and electronic conversations over time. Teachers can browse the database to review both their students' emerging understanding of key concepts and their interaction skills. The COVIS project developed a networked hypermedia database, the Collaboratory Notebook, for a similar purpose. The Collaboratory Notebook is divided into electronic workspaces called notebooks that can be used by students working together on a specific investigation. The notebook provides options for making different kinds of pages: questions, conjectures, evidence for, evidence against, plans, steps and plans, information, and commentary. Using the hypermedia system, students can pose a question, then link it to competing conjectures about the question posed by different students, and to plan for investigating the question. Images and documents can be electronically attached to pages. Using the notebook shorten the time between students' preparation of their laboratory notes and the receipt of feedback from their teachers. Similar functions are provided by Speakeasy, a software tool used to structure and support dialogues among engineering students and their instructors. A variety of computer-based cognitive tutors have been developed for algebra, geometry, and Lisp programming. These cognitive tutors have resulted in a complex profile of achievement gains for the students, depending on the nature of the tutor and the way it is integrated into the classroom. Another example of the tutoring approach is the Sherlock project. a computer-based environment for teaching electronics troubleshooting to Air Force technicians who work on complex systems involving thousands of parts. A simulation of this complex system was combined with an expert system, or coach, that offered advice when learners reached impasses in their troubleshooting attempts, and with reflection tools that allowed users to replay their performance and try out possible improvements. In several field tests of technicians as they performed the hardest real-world troubleshooting tasks, 20 to 25 hours of Sherlock training was the equivalent of about 4 years of on-the-job experience. Not surprisingly, Sherlock has been deployed at several U.S. Air Force bases. Two of the crucial properties of Sherlock are modeled on successful informal learning. Learners successfully complete every problem they start, with the amount of coaching decreasing as their skill increases. And learners replay and reflect on their performance, highlighting areas where they could improve, much as a football player might review a game film. When the geometry tutor was placed in classes in a large urban high school, students moved through the geometry proofs more quickly than expected by either the teachers or the tutor developers. Average, below average, and underachieving high-ability students with little confidence in their math skills benefited most from the tutor. Students in classes using the tutor showed higher motivation by starting work much more quickly, often coming early to class to get started and taking more responsibility for their own progress. Teachers started spending more of their time assisting individual students who asked for help and giving greater weight to effort in assigning student grades. A large-scale experiment evaluated the benefits of introducing an intelligent algebra tutoring system into an urban high school setting. An important feature of the project was a collaborative, client-centered design that coordinated the tutoring system with the teacher's goals and expertise. The collaboration produced the Pittsburgh Urban Mathematics Program, or PUMP, curriculum, which focuses on mathematical analysis of real-world situations, the use of computational tools, and on making algebra accessible to all students. An intelligent tutor, PAT, or PUMP Algebra Tutor, supported this curriculum. Researchers compared achievement levels of 9th grade students in the tutored classrooms with the achievement of more traditional algebra classrooms. The results demonstrated strong benefits from the use of both PUMP and PAT. It's easy to forget that student achievement in school also depends on what happens outside of school. Bringing student and teachers in contact with the broader community can enhance their learning. Universities and businesses, for example, have helped communities upgrade the quality of teaching in schools, and engineers and scientists who work in industry often play a mentoring role with teachers. Modern technologies can help make connections between students in school and out-of-school activities. For example, the Transparent School uses telephones and answering machines to help parents understand the daily assignments in classrooms. Teachers need only a few minutes per day to dictate assignments into an answering machine. Parents can call at their convenience and retrieve the daily assignments, thus becoming more informed of what their children are doing in school. Contrary to some expectations, low-income parents are as likely to call the answering machine as are parents of higher socioeconomic status. The Internet can also help link parents with their children's schools. School calendars, assignments, and other types of information can be posted on a school's Internet site. School sites can also be used to inform the community of what a school is doing and how they can help. For example, the American Schools Directory, which has created Internet pages for each of the 106,000 public and private K-12 schools in the country, includes a wish list on which schools post requests for various kinds of help. In addition, the ASD provides free email for every student and teacher in the country. To make the most of the opportunities for conversation and learning available through these kinds of networks, students, teachers, and mentors must be willing to assume new or untraditional roles. For example, a major purpose of the Kids as Global Scientists research project, a worldwide cluster of students, scientist mentors, technology experts, and experts in pedagogy, is to identify key components that make these communities successful. In the most effective interactions, A social glue develops between partners over time. Initially, the project builds relationships by engaging people across locations in organized dialogues and multimedia introductions. Later, the group establishes guidelines and scaffolds activities to help all participants understand their new responsibilities. Students pose questions about weather and other natural phenomena and refine and respond to questions posed by themselves and others. This dialogue-based approach to learning creates a rich intellectual context, with ample opportunities for participants to improve their understanding and become more personally involved in explaining scientific phenomena.
Technology has offered new insights about the role of teachers in promoting learning. Technology has broken down the barriers of traditional student-teacher roles, and using computers in the classroom creates an interesting situation where both the teacher and students can be novices. Let's take a look at how technology has changed teacher learning. Traditional roles where teachers possess knowledge and students passively receive knowledge has been permanently changed with technology. Teachers and students now work cooperatively to share knowledge, thus redefining social authority and personal responsibility in learning. In order for teachers to stay current with technology, they must work collaboratively and establish a partnership with fellow teachers, students, parents, community, and the computer industry. Teachers also need more time to learn, so they can reflect and participate in discovery. Lastly, they need advisors rather than supervisors to create a partnership in learning. Internet-based communities have become an increasingly important tool for helping teachers learn and network with one another. These interactions help teachers share information about best practices and provide support. Some example communities are LabNet Project, the Quill Network, and the Hume Bio Project, all which helps teachers to learn from each other. With new advances in technologies, teachers have multiple opportunities to learn in this environment. So, where do we go from here? In this presentation, we have had the opportunity to see how technology has enhanced learning. Technology is an important tool that has great potential to increase access to knowledge and promote learning. Essential to developing quality learning with modern technology, there needs to be a solid framework involving all four learning environments. In addition, teachers need to keep up with current learning theory, know about technology, and become educated on how to use technology effectively. We hope you have enjoyed this presentation. You can review additional resource information on the next two slides. Thanks for viewing our presentation.